Okay, my friends, so this video is going to drill down on why that repeated savings formula actually looks like it looks, which is, if I remember correctly, it's 1 plus APR over N to the N times T minus 1, which a lot of you were asking about, which I think is a great question, over APR over N. Okay, so the basic single deposit savings account that we looked at in class the day before made perfect sense, and that you can see elements of it in this one. But as soon as it becomes a multiple deposit, you're repeatedly paying into the deposit or the account over and over again, it gets a lot more convoluted. It looks like this instead. And a lot of you justifiably ask, like, well, why does it do that? Great question, and hopefully this video, it's going to be some algebra, just heads up, it's going to be some algebra, but this video will break down where that formula actually comes from. But in order to break down where it actually comes from, we're actually going to go all the way back without a formula, and we're going to build it up from the beginning. I am going to offer one idea that's going to make the algebra go down easier. So this formula is set up in such a way that you could have any number of compounds per year. That's what N stands for. So you take whatever the APR is and you make it be that divided by the number of compounds is the actual percentage that's applied every period. To make the math easy, I'm going to simplify this whole thing down. I'm still going to call the amount of the account A. There's nothing wrong with that. The payment, rather than having PMT, I'm just going to call it P for a payment that we're paying in. Now here's what we're going to make it a little bit easier. We're going to have it only compound once a year, which means the whole formula is going to look like this instead. Mathematically, it doesn't matter. The same algebra I'm about to do on compounding once a year, I also made the APR just equal to little r, just to make the math easier. Or to make, it's not the math would be the same, it just makes the math easier to see. With fewer letters in the variable, it's going to be a lot of algebra anyway, but with fewer letters in the formula, I think it's just going to be easier to see the steps that we have to do to get from saving money into this form. So bear with me here. The math that we do to get that will be exactly the same math that you would have to do to get that. So let's do it the easier way. Okay, so let's just keep track of this. We're going to keep track of year after year. What happens when we invest money into this account? So the amount in the account in year one, if I remember correctly, the assumption we make in year one is that we just stick the money in, but we missed the interest payment in that first year. So the first year is just, you put the money in and it just sits there. Some folks call that year zero, and that's okay too. That just means we're going to be off by a year in our savings account. But in reality, as we've talked about, generally speaking, we change our saving habits as we age. So being off by a year here or there is not the biggest deal. And algebraically, it doesn't matter either. Okay, what happens in year two? Well, in year two, two things happen. First, the amount of money you had last year gets interest applied to it. This is what we studied previously. The 1 plus R, the 1 brings forward the principal from last year, and then the R is the interest that we get added onto that principal. So that's the first thing that happens. And then we make another deposit. But that deposit happens after the interest. So the interest from last year, this P, gets the interest added to it. This P does not, because the interest happened in between this one and this one. Okay, good stuff so far. What happens in year three? Now here's where it gets interesting again. We can lean again on what we did in the last class. This guy here, this piece right here, already had interest applied to it once. So we're going to apply it again. Which means we can just take this and square it, because it's really this times 1 plus R again, which means we have squared that 1 plus R in that first piece. This guy here from last year is going to get his first interest payment. And then this guy here on the end is just the deposit that we make. Now take a look at that. Hopefully you're starting to see there's some really cool stuff happening here. Let's go out to year 4. Maybe you haven't seen it yet, that's okay. Year 4, piece by piece by piece. Each of these guys is going to pick up an interest. This is going to be 1 plus r cubed. This guy is going to be 1 plus r squared. This guy gets his first interest payment. And then once again, we've got that p on the end. Hopefully you're seeing it now. If you kind of line it up like this kind of matrix triangle looking thing, you can really see what's going on. Now, we can keep going. I don't think there's any need to. We don't have to keep going. So what we can do is we can ask ourselves, okay, so what happens if we pump this out t years? Which is the whole point of the question, right? We want to know from that formula over there, what happens after t years? How much money is in it? Well, the first thing we have to do is we have to think about what this matrix triangle is going to look like. Okay, so hopefully you notice something here. The power on this first term, as we go up, is always 1 less than the number of years. So when the number of years was 4, that was 3. When this was 3, that was 2. When this was 2, this was 1. And when this was 1, this is technically 0. I mean, I didn't write this, but that's technically the 0 power. Usually when I write that, students get upset with me. So I'm not going to write that. Take that away. There we go. Okay, so if it's always 1 less than the number of years, I can write this as 1 plus r to the t minus 1. If I knew what t was, I could subtract 1 from it and get it. So if t was 20, that'd be 19. If t was 30, that'd be 29, and so forth and so on. Now, hopefully you're noticing the powers up here are then decreasing by 1 as we go. So the next term here would be p times 1 plus r to the t minus 2. And then there'd be a 1 plus r to the t minus 3, and then a 1 plus r to the t minus 4. And we keep going, and eventually you'd end up dot, 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 because we don't know how many years they are. T is a variable, so we don't know how many years they are. Eventually you'd end up with, notice how all of these end with like squared, 1, 0 power. Squared, 1, 0 power. Well, this one is 2, assuming that t is bigger than 3. It's going to end up with 1 plus r squared, 1 plus r, and then plus that final deposit there. So after t years, that final deposit goes in, and you don't get any interest. And then I guess at that point you pull the money out of your account. Awesome, fantastic. Now all we've got to do, all we've got to do, is show that that line right there equals that over there. And I know what maybe I know what you're thinking. Maybe you're thinking like, wait a minute, this thing has a bunch of things added together with an ellipsis in the middle of it, and that thing doesn't. Very astute, my friends, very astute. Now I'm going to tell you a story, and we're going to answer, or we're going to address that point. We're going to come to this sideboard over here while I tell you this story. Years ago, when I did my undergrad work at University of Delaware, I was lucky enough to have a gentleman by the name of Dr. Peter Monk. He was adorable, as you can see. And he's this great dude. He's English. I'm pretty sure that he's one of the reasons I picked up my little English accent. Right, I don't think he was from London though. This is more like a Nigel or Billy Bragg. But Dr. Monk was teaching me about something called geometric series. And this is an example, you don't have to know this, but this is an example of a geometric series. So what I'm going to do is, I'm going to write that last line, which was p times 1 plus r to the t minus 1 plus p times 1 plus r to the t minus 2. And then I'm going to go dot, dot, dot again because there's no reason to write them over and over and over again. And then you got a p plus 1 plus r. I'll do the squared, and then a 1 plus r. And then finally that last p on the end. Now this, technically speaking, is A, how much we have in the account after t years, right? That's what that is. And Dr. Monk was teaching us about geometric series, and this is an example of one. And he said, there's a closed form for geometric series. And I was like, what? Like, you can actually, like, get rid of those dots and just write this as, like, something over something? He's like, yeah, of course. I said, of course? What do you mean, of course? How would you do that? And he said, well, are you willing to take a little journey with me? I said, sure. Yeah, this is after class, because he had given us the formula, and we had kind of looked at it in class, and I don't know, I've always been one of those students that always wants to know why something happens. Like, where does that formula come from? So, bless his sweetheart, what Dr. Monk said after class with me one day, sat and said, well, let's explore. What would happen if you took everything in this equation and multiplied it by 1 plus r one more time. I said, like going one more year? He's like, sort of, except you're not going to do that last deposit. I said, all right, so would it look like this, Dr. Monk? You take A, multiply it by 1 plus r, that's good. This would get multiplied by 1 plus r, which would raise that by 1, so that would just be 1 plus r to the t, because if you multiply this by 1 plus r again, it actually ends up thinking it's going one more year, which would get one more compound to go to t. This would become 1 plus r to the t minus 1, because it goes up 1. The next one would be t minus 2, and so forth, and so on, and so forth, and so on, plus dot, dot, dot. This one would actually become cubed. This one would be squared, and this one would just be 1 plus r. And then I said, and you told me don't write the plus p at the end. He's like, Roll, don't do that, because if you put a plus p on the end, you've changed the equation. I said, that's a good point, actually. If I multiply everything by the same number, the equation is still the equation. Okay, good. And then I looked at him and I said, well, what the hell good was that for? I mean, like, now I've got twice as much on the board that I had before. It's no, I mean, look at that. It's a mess. And he said, yeah, but we could make it less messy. And I said, how? Possibly. And he's like, subtract those two equations. And I said, like what? Like this minus this? He said, yeah. I said, okay, I'm trusting you, Dr. Monk. So I did A times 1 plus R minus A. So that's just this minus that. And I looked at that and I kind of scrunched my face up and I said, all right, we'll go with that. And then I started looking at, I took a step back, as he often encouraged me to do. Take a step back and look. And I started noticing something. I'm like, oh, wait a minute. I see something. You see this guy right here, this t minus 1? There's also a t minus 1 down here. So if I subtract everything up here minus this, this is going to cancel that. Ooh. And even though I didn't write the next one here, there's going to be one there that's going to cancel this one. Ooh. And this one over here cancels this one over here. And this one right here cancels that one right there. And that one, if I had written this one back far enough, would cancel that one. As a matter of fact, everything in this equation would cancel everything in this equation except for two things. And the one is, I don't know why I wrote that in red, I apologize. The first one that doesn't cancel is just this thing out front, p times 1 plus r to the t. And the last one that doesn't cancel is that plus p that's out there. But since I subtracted, it's going to be minus p, like that. Ha! Now, as soon as I saw this, I realized where the formula behind us came from. This formula over here, you might not see it yet, and it's okay. But I started seeing it as soon as I got to this step. And there's a couple more little algebra moves we're going to do to make it draw out. First thing I'm going to do is I'm going to deal with this side over here. I'm going to multiply this a in to get a times 1 is a plus a times r is a times r minus a. Now that a and that minus a knock each other off, and you're left with just a times r. Okay, so that's good so far. A times r. We're going to leave that right where it is for a moment, and then we're going to deal with this side over here. This side over here is a little bit more wonky. And remember on this side, when I multiplied the a in, I could also pull the a back out and get back to this form. And that's what I'm going to do on this side. I'm going to pull this p out of this piece, and I'm also going to pull that p out of that piece. Now when I do that, I leave 1 plus r to the t right here, and if I pull that p out, I have a 1 right there. So just like before, the 1 stands for the principal. Now if you look at where we are, I'm going to rewrite this one more time. If you look at this, if you divide both sides of this by r, you get a, which is the amount in the account after t years, is p times 1 plus r to the t minus 1 all over r, which, my dear friends, if you wander over here, is exactly the same formula that we were trying to show that it equals. And I just think that's incredible that, I mean, I know algebra is not a big part of this course, and it's not. It shouldn't be. Math 105 should not be algebra based. But enough of you have asked the question, where does the formula come from, that I wanted to make sure I addressed it properly. And I hope that myself and Dr. Monk have done an okay job. We'll see you in class.